Okay. Good afternoon, everyone, and we are very happy to have Professor Frisch. I hope my pronunciation is correct. I don't know how you pronounce it. My apologies if I am not pronouncing correctly. In today's series, which is supposed to be a webinar, so that's why probably more people are online than offline. But since actually this webinar series started during the COVID period, so all the speakers were always online. But now since the COVID is presumably gone and probably we'll have more speaker in person, so I request the organizer to change the name of the series. We can just call it seminar series, because if you just always announce like webinar, then people will expect it to be on. So with that, we are very happy to welcome you here. And he did his PhD in 1967 from Sorbonne University and mentored by Robert Kirchner, who was former assistant to Albert Einstein. So I'm sure you have many memories and stories which you have heard from him about Einstein. And he worked in CNRS in Nice, and but he retired in 2006. And currently he is the director of research emeritus at CNRS. And he is most well known for his contribution in the field of turbulence and fluid dynamics, the HP model, where the first acronym F is due to this gentleman, was a game changer in the field, providing a way of accurately simulating the behavior of actual fluids. The another probably worth mentioning contribution of him in this field is his work with Parisi, the Nobel laureate of 2021, on the analysis of fine structures of turbulent flows. And he has several accolades to this grade. I will just mention two very recent ones. 2010 International Prize of Applied Mechanics from Turin Academy, and 2020 Euromech Prize given by European Mechanics Society. And title of today's talk is very fascinating. It's Leonardo da Vinci, Andrei, Kolmogorov, and Giorgio Parisi, the energy decay of turbulence from Leonardo to multifractal theory. And once again, I welcome to SN Bose Center. And it's a pity that I have to leave with this being webinar. This talk will be recorded, so I believe I can have the pleasure of listening it afterwards. So please, the floor is yours. To microphone.
Okay.
Yeah, the point is, I don't know how they can do it, but yes.
I told them it's impossible for me to speaking with this noise.
Yes. Yes. So then you just you just stop the online thing. Whoever has joined, they have joined. Because at certain point you have to stop. So you just stop it. How many people have joined so far? So he gets irritated by this noise, which is irritating.
If notification is not possible to stop, the notification.
How many people have joined? Can you check?
नहीं और नहीं हुआ कितना है उसमें 27
At least stop for it. So you will not get that much.
The sound has to be adjusted to my voice.
Yes, that they will.
That they will do when you start giving your lecture, they will
They will.
calibrate it. We
They
can
will.
hear your speaker. That's not a problem.
That's fine.
Yeah.
stop कर रहे हैं ठीक है Somebody blocking that joining. Someone is blocking that joining, so someone will be able to join from next corner. So,
No, there will be constant sound.
Alert which comes when people are joining online from webinar. So that room for joining will be closed in 1 minute. So
Oh,
that you don't
I
get
got
that.
it.
And we can hear you on the speaker. Don't worry.
नहीं मिल रहा है
That's fine.
তো হোস্টিংটা ওখান থেকে করতে পারো না
বস্তু ওখান থেকেই বলছে
তাহলে এখানে তো ঠান্ডা হবে
মিটিং বন্ধ করে যাচ্ছে অপশন নেই
তাহলে আমার
কোথায় আছে
ইন বিটুইন অপশন বক্স অপশন নেই
আমি দেখতে পারি এখানে
আপনি যদি আসেন
Excuse me. Excuse
Yes.
this to make that test on my voice.
Yes.
So then make sure that you hear something like this problem.
Sure.
So
My mic is not working.
I cannot speak too loud.
Sure, we can hear you.
No. Stop it.
Done.
Why not use the data that stand?
Let me see. No, you tell me if it's fine.
Can you hear it?
Let me give you numbers.
Can you?
3, 2, 1,
3, 2, 1,
1, 7.
417.
Okay. Thank you very much for your invitation. It's a great pleasure of being here. For the first time in Calcutta, I've been in here many times. First, I visit Calcutta.
Maybe you can come over. This input.
Many of my friends.
Mic is on.
Microphone.
Oh,
Maximum sound. Maximum volume there is not.
they're just increasing the audio for the online. Don't worry, you continue. They're just yeah.
Excuse me, if you were speaking there, sorry, I cannot speak.
No, now the mic is starting to work.
जब नेक्स्ट पे joining आप कौन जाना
Hey,
I said, no,
you have to speak outside.
Yeah, otherwise I
Yeah,
have.
now.
That's not a need for me,
Yeah.
sorry.
So now it's good. Now
Yeah.
they can play.
All right. So, as I say, many of my scientific friends are from this place. This is my first visit here. Okay, it was a great thing to see the museum up an hour ago, so it's a fantastic place. Okay, so let me start here. So the title, of course, is Leonardo da Vinci, Andrei, Kolmogorov, and Giorgio Parisi. There is a star here, which refers to the Nobel Prize of 2021 which Giorgio Parisi at the same time as Mana and Klaus Hasselmann for ground breaking contribution to our understanding of complex systems. So let me go to the that's it. Okay. So now Leonardo and turbulence. I remind you that Leonardo was born in 1500. Correct. When Leonardo turbulence did take place, roughly between 1505 and 1550. That is the late period of Leonardo da Vinci, who lived rather alone. His interest in turbulence came only at a later age, and as you will see, that is an important discovery that was made very recent. Yeah. Now, the very similar aspect of turbulent motion in air or water was already interested under the word and philosopher Lucretius at the time of the ancient Romans. That's 2,000 years ago. In the early 16th century, Leonardo da Vinci, born and dying in 1519, studies the decay of elements in rivers, such as indicated in this figure. Leonardo called such flow turbulence. That was some, okay. A name used before only for random motion of leaves pushed by the wind. That's a very different concept. To the best, my knowledge, he was first used turbulence in its modern names, but with Giorgio Parisi, we will see if this is true or it's just a myth. Yes, so far, that's useful. Yeah. Now, I can operate that. That's okay. Yes. So, let me tell you a few things about Leonardo. That's typically one doesn't say Leonardo da Vinci, but just Leonardo, and everybody knows what that means. Yeah. And something called the Codice Atlantico. Very strange name. So I have to introduce you something called Pompeo Leone, who lived significantly after Leonardo. In the year 1608, and who got all of a number of manuscripts of Leonardo. By the way, all the manuscripts are in Italian, not in Latin, because Leonardo was a sort of illegitimate child. He did not have the right to study Latin. He just was studying mathematics. At the time, that he considered much more important than may have been, but saved him. I'm sure nobody's here against mathematics. If you have to learn the ancient language, perhaps you will speak Sanskrit rather than Latin. So However, Pompeo Leone he had many sheets. Precisely, there were more than 1,000 sheets, double-sided. And he assembled them more or less by his taste. And his taste was not that of a historian of science. And so they had it mostly wrong. But nobody knew what the correct order was. It took a very, very long time until a specialist, Leonardo, could clean this up. Because from the time of Leonardo, one could have inferred that the work of Leonardo on turbulence started just please. And close the door because there is more noise coming in there. That's useful.
Actually, the AC is not working, so we'll have to keep the doors.
What is this?
The air conditioning is not working.
I find it is a blessing that it does not work.
But if we close the door, it will melt down.
Okay.
You have to keep it
Okay.
open.
Okay. I hate the air conditioning solid. Yeah. Right. Right. Now, see. Windows open.
So that's why we kept the door open to have a
Yeah.
circulation.
Just try to there. Yeah. So Pompeo Leonardi put some slides, as we call them, near the beginning of the Codice Atlantico, suggesting perhaps that he worked on it before leaving his home place for Milano, so maybe prior to 1480. That is completely wrong. So let me introduce you to the work Augusto Marinoni. Now, Marinoni died rather recently, in 1997, and he was a Romance philologist from Milano, but one of the greatest specialists in Leonardo da Vinci. For this, he used his deep understanding of the various phases in Leonardo's activity and also the evolution of his handwriting. Actually, this is the left hand, everything is the left hand. Yeah. Now, according to Leonardo's late 1990 work, published a few years ago, 2017, the text of Leonardo about the decay of turbulence, about which I will speak, is not at all dated from before 1980. It was probably from 1505. Very different date, 25 years later. Now, what is very interesting, that starting 1504, Leonardo was very busy planning to divert the course of the Arno River from Florence in order to deprive the town Pisa which is along the Mediterranean. And deprive it from a lot of water. At that time, various Italian cities were fighting each other, sometimes really ferocious. And Leonardo never tried to hide the fact that he was very interested in application, be they military or completely innocent, like airplanes and things like that. So, what is amazing to work on the thing that he did in 1505, which I will discuss in a moment, is on the decay of turbulence, how it decays in time. And you will see this problem is still not solved. And as some ideas, it's not so solved. Turbulence is one of the longest classical systems because quantum mechanics was not invented at that time. Classical physics was beginning to emerge, just a little. Yeah. Actually, I will even move away so that I can see the whole thing. On the left, you have the hand. Is there no way to?
No, this is the Google Meet doesn't allow you.
Huh?
Google Meet doesn't allow you.
I didn't get that. I've never heard such a thing like that.
No. If you are in front of the computer on Google Meet, it will play this because of the webinar. Like Zoom has this button, so there is no way to suppress it.
Oh,
But now people will not join anymore very frequently.
I see.
So it's
I
Google
see.
Meet.
That's a very stupid thing.
Yeah. Google.
Not everything done by God is clever.
Of course.
Yes, of course. So that is the right thing. Now you can't see a thing there, but if you turn it around on a computer which is triggered, then you will see there is a word like turbulence here and all the turbulence there, etc. And you can start reading it. So if you read it in the Italian of that time is not very far from current Italian. So here it's translated into current Italian. Dove la turbolenza della quasi genera, dove la turbolenza della quasi mangente blu, dove la turbolenza dell'acqua si posa in English, where the turbulence of water is generated, where the turbulence of water maintains for long, and where the turbulence is to rest. Now, that is the very first description of the decay of turbulence. How did he do it? One has some reasonably good idea. Namely, Leonardo, he used all the mathematics that was known at the time, but even the exponential thing was not invented. So they could, there's no way Leonardo could say, for example, that the energy of the turbulence would decay exponentially or non-exponentially. These things did not exist at the time. So he used the best words that he had. And the key word was the turbulence maintains for long. Even you, because you know exponentials, this is not an exponential. That's the best we could do at that time. And as you will see now, I know enough about the decay, not the exact primary number, but it's algebraic t to the minus something. But that was not enough for Leonardo. He needed to observe things. And since he was very clever, he not only jumped into the Arno River, but made special glasses of this kind. This is his own design to look at the eddies, as we call them, because now we call them rather eddies than turbulences, but of course he called them turbulences. And he was able to do that very frequently. And at the time when he was trying to find out if the course of the arrow could be diverted, instead of going to Pisa or some other places, and deprive Pisa of water, which would be a big military success. Actually, after several months of such experiments, Leonardo concluded the cost of the whole thing would be tremendous. And it was too expensive. So he abandoned this thing. But of course, we still have all this writing there. Now, we will leave now Leonardo and look who else has studied this problem after Leonardo. For this, we have to wait more than 4 centuries. So now these names are probably familiar to you. Hermann, the great fluid dynamicist, who wrote a paper in 1939. Kolmogorov, paper 3 years later. And Prof Reed, whose name may not be familiar to you, but I will show you that Prof Reed had a major contribution to this. That will be perhaps the crucial point of my seminar. So, Hermann had a feeling that turbulence was decreasing very slowly. He agreed there with Leonardo. And of course, with modern mathematics, he could imagine something like t to the minus something. No problem. But which something? That's a terrible thing. All the people who studied this had it wrong. First, Hermann, on the way, they write the power law. Then, 3 years later, Kolmogorov studied the paper of Kalman, and he found that there was a horrible mistake. I mean, suppose I tell you that A plus B is C plus D. Even if you're a chemist, you understand me. Okay. And then I want to get A out of this. Then you see C plus D minus B. Kolmogorov put the plus. Kolmogorov found the mistake, corrected it, and then used a result which had been obtained 1 or 2 years before, another Russian, Lubyansky, a certain invariance law of turbulence than Navier-Stokes. And Kolmogorov predicted that it would decay like T to the minus 10 over 7. Aha! This was even worse than this cake. This great man, even Einstein, sometimes made mistakes. So, okay, you have to be prepared for this. So,
But this invariance,
Amen.
this invariance was not assumed by Karman.
I can't hear you.
Was the invariance assumed by Karman?
No,
That was
I couldn't remember. You, because the work of Lagiansky after Karman. So, so we're talking about 41. It took 9 years to find that Kolmogorov was wrong. And the people who found that were Proudman and Reed. Now, Proudman was the son of the even more famous Proudman who worked with Taylor and two-dimensional flows and things like that. Reed was a student of his, but before that, he was in the United States and he worked with in the United States. So they worked on the law of decay and found that the Lowriansky invariant was not invariant, and it was wrong. Aha. A few years later, the Japanese physicist Ogura showed that the method that Proudman and Reed were using was making use of the so-called quasi-normal approximation. What is that? First of all, I remind you that what some people call Gaussian, other people Laplacian, other call it normal, etc. That's all the same. So it depends on the language that you use. And so if the initial data for the Navier-Stokes flow or the Euler flow are Gaussian, they are not going to stay Gaussian because the equations are non-linear. And the method that was used by Lubyansky was cheating, that the Gaussian approximation, which is exact, for example, at the initial data, is still approximately true, and not too large times. And however, Google showed that this eventually lead to complete impossibilities, namely negative kinetic energies and things like that. So this was found here in 63. And a very nice paper written in English in the Journal of Fluid Mechanics. So everybody said, oh, the QNA, the quasi-normal approximation, is no good. Not true. It took many years to find the particular use of Brauman and Reed of the quasi-normal approximation is correct. This is hardly published. Actually, in a book of mine, if you read between lines, you will find it, but not really in detail. What is happening is that if you start with from Gaussian data, then you can use Feynman graphs to find how the solution develops in time. Well, I have Feynman graphs, and you then start counting, and if you do it well right, you will find that the dominant interactions are interactions between, you see, I have to, I think because I'm two hands. You can do everything in Fourier space, and the peak of the energy happens at some wave number. And if you can take two wave numbers nearly opposite and you add them, then the sum will be very small. And these are called non-local interactions. And it is only there that it is matters whether the energy is or is not positive. And with the QNA, it is positive there. The rest of it doesn't matter. Therefore, the use by Brauman and Reed of the QNA was correct. So they proved that Kolmogorov, by applying the Lorentzian invariant, was wrong. And that it was realized only very recently. So, so both Kalman and Kolmogorov were wrong. So what is then the correct answer? We don't know yet. We know what is wrong. We do not know what is right. So how can we do something there after so many years after Leonardo? So let me first tell you about some important steps that were taken after the 1940. Kolmogorov had two theories. A 1941 theory, which is a self-similar theory, within which you can imagine that the eddies are, as the left side, there are large eddies packed together, and then smaller eddies also packed together, etc., etc. You can easily imagine that this whole thing continues indefinitely, given the limit of the infinite Reynolds number, and then you can infer from that that there is a self-similar structure for the turbulence. That is what Kolmogorov proposed in 1941. which is not completely wrong, it's only partially. Then much later, we found a new theory for which Monroe showed that it is fractal. So that the large eddies are the same here, but then they become rarer and rarer and rarer to plenty. And there is basically nothing turbulent in between. So there's been a lot of work on that, at least phenomenology. And so yeah. After first attempts to have a simple fractal theory with a single set of fractals, the experimental work of people working in France, but they were not all French, or when they were from all kinds of nationalities, was indicating that this doesn't work. The data which were obtained by us in the Garden of California were communicated to me because I was a friend of them 1 year before publication, and I worked on it with Giorgio Parisi. And we found that the only thing that can explain the data was the multifractal assumption. Now, that is a rather strange thing because this means that there is not one type of fractal, but many, maybe infinitely many. I found this very strange at first, but the data are very solid. The experimentalists were very good, so we accepted this somewhat in Parisi rather gladly, and I slightly reluctant. Parisi was right. It turns out that the theory of multifractals has developed as a very nice niche for this theory. So let me turn to multifractality and Warner's theory of large deviations. Actually, this morning I discussed with one of the people who perhaps here, they wanted to understand multifractality in chemistry and so on. Now, one of the things that are crucial for the experiment of this is to calculate what Kolmogorov called structure function. That is, these words. Structure function are just increments, velocities, raised to some power, an average. And how does this scale, this separation? And what is found is that it could easily vary like power laws, but if one uses multifractal assumptions of having all kinds of fractals, then a simple deep shuttle pointed relation one finds that the structure function has an exponent which can be described this way. Lo and behold, the exponent of the structure function is the Legendre transform of Foucault dimension. what is the co-dimension? It is dimension space 3 minus the fractal dimension. And if you look at that, yeah, this is simply a rule of small. And what Claire showed us that when you want to handle very large deviation from Kolmogorov, sorry, from nonsense. Yeah. Then I have to take whatever machinery is available there. And that's the role of this was. Then Leonardo was first to do this, but he didn't do it for turbulence. He did it for finance and big crash of companies and so on in Sweden. And he was a very good friend with the French mathematician. And for him, this was very practical thing. He wasn't afraid of applying it to predicting the future of companies. And that was correct. And there is now the same thing has been much more later applied to turbulence, starting with the paper with Parisi. And it is something which was a revelation for me, because I thought that the experimenters had been wrong. It was far too complicated. And then in studying Claude's theory, I found they were right. Now, you can just look at the statistics of multifractal data, dozens and dozens of fields. It's a very important concept. Discovered sort of by chance. And let me first point out something. There is a paradox. After all, the equations of Euler and Navier-Stokes are well-defined mathematical objects. Can one then apply standard mathematics to them and find what is right, what is wrong? No. The mathematics of the three-dimensional Euler, three-dimensional Navier-Stokes equation is still really missed. So for turbulence, three-dimensional turbulence, nothing is really proven now. Does it mean that we have to wait 4 centuries before we can make some progress? Not necessarily. If we can find another subject sufficiently close to turbulence that we can apply real mathematics. And what seems to be the right thing is the famous bird. What is that? What's that?
Your thing moved. Your thing moved. Yeah. Yeah. It's fine now, Uriel. Yeah.
আপনি নিচে লাগলেন তাহলে শোনা যাবে না উপর দিকে না হয়তো চলে এলাম
Stay away from the screen.
And also don't come too close to the speaker because it will resonate.
Yes, indeed.
Feedback.
So the Burger's equation is just one dimensional analog. The Navier-Stokes equation has more or less the same family. And I had hoped that the Burger's equation would allow us to do such things. However, Burger's equation has shocks, and that they ruin everything. There is nothing significantly fractal. There is a double staircase with a single dimension. So the question, what can I do with the Burger's equation? At that time, I would notice that the real question was the large scale and the decay of turbulence. That involves very large scales, not small scales. So when I find what is happening at extremely large scales and not at small scales. Yeah. So here is the Burger's equation. Of course, it's just very new look, very much like the Navier-Stokes equation, except that it's one dimensional, there's no pressure and so on. And there is a very nice result. One doesn't know exactly who found it, maybe numbers or something. That one can find the potential for the velocities minus the gradient of the potential. Phi can be expressed in terms of the initial data completely explicitly by something which actually, so you can easily handle it, it is a called for transport. And so can one use this thing perhaps to prove that the large scale dynamics, the Burger's equation, is multifractal. And let me first all the work starting from here was done is Costa Harding, the Colombo, Raoul Pandit, in Bangalore, and the Ankaroi also in Bangalore. And of course, one of them is from Karnataka. You know, Raoul is here, and Ankaroi was closer to China. It's native change. Okay. Yeah. Something very strange happens with the Burger's equation. When the initial data is of the potential is either Brownian motion or a cousin, therefore, called fractal Brownian motion, which is not too difficult to different motion. And what then happens is something very strange when one calculates the maximum effect forward. So basically, shift this thing by a carbon, and what you get is something very strange. And find a Kolmogorov swirl. Now you know what is happening when you have a nice curve going and you want to get its convex swirl, then in places it follows a thing and then it jumps, and it follows, it jumps, etc. With Brownian motion, it doesn't do that. It has only individual points because round motion is not differentiable. You cannot follow something. You have to jump. The same thing happens also in fractional ground motion. And the consequence is that in a Lyrian space, the solution is very boring. It has shocks and ramps, very simple. And if one were to investigate the small scale thing, it would be completely trivial and follow what some people have here. This is that multifractal type. But that is not what one wants to follow the large scale behavior, the large thing. There's a big problem. Yeah. This is just a reminder of what is happening rigorously this now, because we're not going to stop from purpose. When the initial data for the potential is fractional round motion, and it's quite boring because at the end you get all the answer. Everything is completely self-similar. And you get a power law in time. Great. But that is not multifractal. That has a single so-called burst exponent. How can you make it multifractal? It took us a long time to try. We tried all kinds of things. How you replace burst and so on. Finally, we uncovered or found that this it doesn't work. And much more recently, we found how to cure all these things. And that's what we need. The best way is to have a graph not of the potential, but of what is called the Hurst exponent. The Hurst exponent of boundary motion is 1/2. But boundary motion can be extended many the coverage between 0 and 1, strictly between 0 and 1. And the Hurst exponent normally is constant. But if you can change it and accept to have hyperbolic tangent. The nice thing about the hyperbolic tangent is +1 here, -1 here, and then you have an exponential transition. You can make them very narrow. But that is the kind of thing that you obtain there. No. And finally, the conclusion. Of the Navier-Stokes equation, and new numerical simulation, so on, but advanced mathematical is premature. For the workers, maybe perhaps, and now we have a feeling that by a mixture of very refined simulations and some heuristic theory, which is not 100% rigorous, but close to rigorous. Perhaps be rigorous for a physicist, but not for a mathematician. Yes, one can get pretty close, particularly when the numerical and the heuristic theory agree. And so our feeling is that in less than 1 year, we can achieve that, but not a complete theory, but a significant progress. And see if the equation is not the fact of the initial data also has the right properties. We already have strong evidence that the Burgers equation, the decay of the law is not t to the minus something, which is not block the straight line. It goes yeah. That can be proven all enormous figures. And so this is ongoing work. And of course, the key people involved in it. Therefore, when one is 2 are in India, 1 in Canada, that is women, and 1 in France, that go between the effects.
Thank you very much for the fascinating talk. Are there any questions? Maybe I don't know. Is there any questions?